So the overall idea, how come you're not taking notes? The overall idea is for stresses in beams, the total stress at a point is the stress due to tension or compression plus the stress due to the bending moment plus the stress due to the shear force plus the stress due to the torque. This one was really easy. So now we're talking about this one. So stress due to bending moment. And the type of stress is the X normal stress. And the formula for it is negative bending moment Y over I. Where Y is the height relative to the neutral axis. Remember, the neutral axis is the plane where on this plane, when you bend this beam, it stays the same length. So there's no compression and no stretching. Okay, so let's think about how this sign works first of all. So let's think about it in the case of a positive bending moment and a negative bending moment. Okay, and let's think in both cases, well, the neutral axis is the middle. Okay, so the neutral axis is somewhere there. And let's think about a point above and below. And then same thing over here. Okay, so in this case, this is a positive bending moment. If you started with couples like that at the ends and went in and calculated the internal loads, you get positive bending moment. So this is a positive value of M. And so what happens if you start at the neutral axis and go positive Y? Okay, so we're going up to the red one. Okay, this formula says for that red point, Y is positive, M is positive, I is always positive. We'll talk about what that is. And so in this case, that red dot should be in compression. It should have a negative X normal stress. Okay, you see that? And then think about what's happening here. Think about that being like the inside of the track. This is the short part. And so that makes sense intuitively. Now this one, go to the blue dot. We're still dealing with a positive bending moment. Y is negative. So all of this becomes positive. And that says that the X normal stress is positive. So it's in tension. And that's what you would expect if you bend it this way. Okay. And everything works the same but opposite in the other case. So now we have a negative bending moment. Um, and so m is negative. If you go to the red dot, y is positive, divided by a positive. So sigma xx should be positive. It should be in tension. And that's what happens if you, to the top, if you bend something that way. And if y is negative, then you have negative, negative, negative. Sigma xx should be negative, and the bottom should be in compression. Yes? Well, really the way you do it is you make a cut and calculate the internal loads. So like if I made a cut here, and the only external load we have is this, and then we have our internal loads. It has to be counteracted by a moment like that, and that's a positive bending moment. No, it's not. That would make it spin, but that's the idea. In order to have equilibrium, you have to do it like that, which is a negative value of m. Yes. Yes, because because of the way that the couples you have to apply to make it do that. Yep. All right, and so that's where the sign comes from. So the sign makes intuitive sense, and that means just trust the sign. I mean, it's always good to have a picture in your head of what's going on, but signs will take care of themselves. And then the other thing we have to consider is we have to know what the limitations are on the shapes of the beam. So beam restrictions. There are 3 of these. Anyone remember any of them? Yes? Are you remembering or are you reading your notes? Okay, yes, straight. Or nearly straight. Prismatic. That was the one I was having trouble with. Prismatic. Or nearly. Those nearly things are sort of a nuisance because it gives you like some wiggle room or whatever, but it's just saying the farther you get from these, the less accurate your results are going to be. And then the last one is symmetric. About the y-axis. So we can do beams with a cross section like this. But we can't do ones like this. Can you believe it? That's bullshit. This one's okay. That's fine because the y-axis is this. Well, it depends how it's, if it's, yeah, right. How it's, it depends how it's oriented relative to the bending moment. But this is the y-axis, so that's the key axis of symmetry. And good luck finding beams like this. All right, so now we need to define neutral axis. and I, which is the area moment of inertia about an axis. And people just call it the moment of inertia. So this, you do need to keep this stuff in mind, or you'll get confused about this versus one that you use in dynamics, which has a lot of similarities, but it measures something different. So the neutral axis. The neutral axis is, for a given cross section, it's parallel to the z-axis, and it passes through the cross section's centroid. That's pretty nice, simple fact. So if you're thinking about, okay, there's this sort of theoretical place on a beam where when you bend it, the length is not going to change, you know, it seems like a lot to expect, a lot to hope for. That's just going to line up with where the centroid of the cross section is. And that's what it does. So if you have a shape like this, there's the beam. There's the x-axis. There's the y-axis. There's the z-axis. Just put the origin at the centroid of the cross section. And then the neutral axis is just the z-axis. And remember, that's for a single cross section. And if you draw the neutral axis for every cross section, here's one, and then go back a little bit, and there's the next one, and there's the next one. What you get is a, like sliding this salami in half this way. You get a plane that goes through parallel with the z-axis all the way back. So what does that look like? Not like that. What? That red is a plane that defines all the neutral axes. What? Yes, it's the XZ plane. I don't think I've ever thought of it that way. Yep. Yeah, that's kind of the that's where things get really messy with the math. But for us, we're lucky. We're dealing with very small deformations. And so we always assume that things look the same before and after the deformation. And so for us, we don't have to worry about that. But as things get more complicated, as you start dealing with bigger deformations, then yes, that's a serious problem. Any other questions? All right. So that's it for the neutral axis. And the next thing we have to define is the area moment of inertia, I, about an axis. And the definition is an integral definition because that the word moment is a mathematical thing that is defined by certain types of integrals. And I, about an axis A, is equal to the integral over the entire cross section of y squared dA where y is, well, let me say this differently. Where the origin is on the axis A. Okay. For us, the axis A is going to be the neutral axis. And so we'll put the origin at the centroid of the cross section and use this formula. I think I did the same thing in dynamics. I'm just going to do one integral calculation, but really we're just going to use formulas. So let's say that we have a beam and the cross section is this. The neutral axis is the horizontal line that goes through the centroid. So we can call that the origin. Then the z-axis is this way. The y-axis is this way. And the z-axis is our neutral axis. And that's our axis A. And so what we're going to do is, for a single cross section, let's say that the dimensions are, let's call that B and this H. And this is the neutral axis. And to do this integral, I'm going to, okay, look at the integral again. We need to divide this cross-sectional shape up into infinitesimal pieces dA, little infinitesimal areas, okay? And we need to do it in a way that, you know, in order for us to calculate this integral, each one of these dAs has to be made up of all points that are the same distance or have the same value of y. Okay, because otherwise, you know, the idea is we're trying to break this up into pieces where we can say, okay, that piece has a y value of this, add that to the next dA, and it has a y value of this. That's sort of always the approach with these kind of integral definitions. Okay, so I'm going to break this up into pieces like this. So this is my piece dA. The width of it is b. The thickness of it is dy. And so the infinitesimal area dA is base times, you know, the height of that little sliver, so dy, birthday. The height, since this has an infinitesimal thickness, this is just our y value here. And so I sub a is the integral from, okay, and why did we define dA like that? Well, since we already have the y's in there, it would be nice to define our infinitesimal area in terms of y, then we can integrate with respect to it. So we found this relationship between area and y. So now, the formula, y squared times dA, which now we have written as b dy. And what are our bounds of integration? Because of where the origin is, we could do it from 0 to h over 2, and then, but let's just do it from negative h over 2 to h over 2. And so we can pull out the b, and we have y cubed over 3 evaluated from negative h over 2 to h over 2. And so that's b h cubed. When we cube that 2, it's an 8. So now in the denominator, we have 3 times 8, so 24. And then minus b times, since this is a cubic, that negative comes through, so we have negative h cubed and over 24 for the same reason. And so we come up with a formula b h cubed over, we have just 2 times, 2bh cubed over 24 is bh cubed over 12. Okay, so what does this say intuitively? Notice not all dimensions are created equal for this. The height of the cross section is way more important than the width of the cross section. Okay, where have we seen something like that before? So last time we didn't start doing the calculation, but I did say that, okay, this is the same piece of paper under the same bending load in this configuration and in this configuration, okay? And the cross section is like this is the cross section, or this, okay? If we hold it like this, okay, then we know that it's very easy to bend, right? It should have a very low area moment of inertia. So look at this formula, and you know what happens when you plug these in this configuration. The base is big, but the height, the thing that you cube, is tiny. And if you cube something tiny, it gets super micro tiny, okay? And so that's why this has no ability to support bending loads like that. But if you take the same material and turn it like this, now the base is tiny, but the thing that you cube is big. And so you get, you know, many, many, many times more resistance to bending in this orientation than in this one. And structures that you make for building, well, not structures, you know, objects that you make to build structures out of, like I-beams, are useful because no matter how you orient them, they have a relatively small amount of material required, but still provide a lot of resistance to bending because you're moving the flanges at the end, you're getting them far away from the center, and you know the integral formula for the area moment of inertia rewards you for getting stuff far away from the centroid. How many people here have ever taken intro to engineering? Anyone? Did you do the bridge crushing thing? Okay, so you probably either sort of intuitively understood this about resistance to bending, or else you sort of figured it out as you went. You didn't get rewarded much for using your material to make the thing wide. You only had to make it wide enough that you didn't get some kind of weird twisting and then it would break the other way. What you're really rewarded for is making it tall, getting the material separated really far from the centroid vertically. And again, it's not really an issue of, I say tall because we're always thinking of these things bending up or down. It's really the relationship between the shape and the axis of bending. But we're always going to do these problems with the axis of bending being like the z-axis.
So now, since this area moment of inertia is going to be important for calculating the stresses due to bending moment,
there are two really important shapes for us.
The formulas for area moments of inertia for three shapes that are likely to.
So let me give you the formulas. The area,
rectangle, a
moment,
circular shape, and a triangular shape. And
of inertia.
Remember that these are the cross-sectional shapes. So
for simple shapes,
when I draw like a rectangle, you have to imagine that the beam, the long axis of the beam, is going perpendicular to that cross-section that I'm drawing. So, okay. Area moments of inertia.
The first one is a rectangle. This is the one we just calculated. There's an L in there somewhere.
For three common shapes, let's say three.
So that's the y-axis, that's
shapes.
The z-axis. We'll say it has a width b and a height h. And if this green is our axis, then I sub a.
And you have to keep in mind that these are all, we're talking about
is 1/12 base times height
a
cubed.
horizontal axis through the centroid.
The second one is a circular cross section.
And I'll draw that on here. But okay, so the first one is a rectangle.
There's y and z. We're dealing with a radius r.
So let's say that the
And
vertical
for this,
length is h, the height.
so z is the axis we're talking
the
about.
horizontal width is b for the
The area
base.
moment of inertia about that
And
axis
the
A
axis that we're talking about
is 1
is the
over
horizontal
4
axis that goes through the centroid. So that's the axis that it would
IR
be
squared.
bending around.
No,
And
IR
the
to the fourth.
formula, I sub A,
That would
like
make
you can
sense
think of
with the units.
this
What are
as
the
A,
units of the
this axis.
area moment of inertia?
I
Yeah,
sub A
meters to the
is
fourth.
1/12 times the base.
And then actually we use triangles a
times the
lot
height
too. I
cubed.
don't have it.
So you
written
can
down
see
here.
that if you think of this area moment of inertia as a cross-sectional shape's resistance to bending, you can see that the height is a lot more important than the width.
We will talk about how to add shapes.
And
So
we're going to take advantage of that.
we'll do
and
it only
engineers take
for
advantage of that
equilateral
when they
triangles,
design
though.
the
Like
cross-sectional shapes of
it
beams
doesn't have
and
to be
things that
equilateral,
have to
just
support
isosceles triangles. And the reason we only care about
the second
isosceles
one is a
triangles
circular
is because
cross-section.
we're restricted to shapes that have those symmetric cross sections.
The axis is horizontal. And
So you
goes through
can
the
calculate
centroid,
the
so
area
again,
moment
that's
of inertia for
the
anything, but
axis.
you can't
And we're
use it in
talking
this
about a
formula
radius
unless
r.
the shape is symmetric about the y-axis.
And the formula
Are we going to
for
really
moment
just
of
go through the
inertia,
pain of
area moment of inertia
calculating this from the
is
integral?
pi r to the
We
fourth
should, right?
over 4.
For a triangle? Okay,
And then the last
I'm not
one,
putting
we're
this
not
in the
going to see
notes.
this as much. I can't remember if there are any problems where we use this or not, but an isosceles triangle. It has to be an isosceles triangle like this because in order to use the formula for stress for a bending moment, in order for it to be applicable, this thing has to be symmetric about the y-axis. So it has to be like that. The axis has to go through the centroid. So there's the axis A. And again, we'll call this B. And this will be H, the height. And the formula for the area moment of inertia about A is BH cubed over 36. Okay, well, you know, we're going to have to deal with beams that aren't any of these three shapes. But it turns out that, like, you know, maybe you'll see the parallel with the mass moment of inertias that we do in dynamics for the people who are in dynamics too. We can build up more complicated shapes out of these simple shapes and use some formula. So there are two things that make these formulas more useful to us. The first one is if a cross section is made up of two or more of these simple shapes, let's say made up of two, but you can obviously like keep repeating this to make it a more complicated shape. So if it's made up of two shapes, 1 and 2, then the area moment of inertia of the combined thing, you know, the area moment of inertia for the combined shape 1 and 2 is equal to the area moment of inertia of 1 about A plus the area moment of inertia of 2 about A. And you can also do that with subtraction. Like if you have a rectangular cross section that has a circle cut out of the middle, you can do it with subtraction. But one thing that's important here is 1 and 2, you have to have those area moments of inertia calculated about the same axis that you want for the combined shape. And so that means that we're going to want it for the centroid of the, for an axis going through the centroid of the combined shape. That's not, in most cases, the centroid of either of these two. So what we need is a way to use our calculation of the area moment of inertia of the simple shape about that simple shape's centroid, and then move the axis that we're doing it to some distance from there, some vertical distance. In dynamics, with the mass moment of inertia, we do that with the parallel axis theorem, and it turns out that we have a parallel axis theorem for this too. So notice that this idea, this first useful thing, this ability to sum moments of inertia, really would not be useful in hardly any cases at all if we didn't have the ability to adjust where the axis was for the centroid. This is called the parallel axis theorem. And what it says is if this is your cross section, well, you can calculate an area moment of inertia for a crazy shape like this. It wouldn't be applicable for our stress calculation, but this is I'm just trying to show that this is the general idea of this parallel axis theorem. So say the centroid is here, okay? And so say that we know the area moment of inertia of this shape about this axis, and say that we want to calculate it about this axis A. Okay, so this is the neutral axis. That's the horizontal axis that goes through our centroid. This is the axis A that we want. And let's say that the vertical distance between those two is D. Okay, then the parallel axis theorem says that the area moment of inertia about A is equal to the area moment of inertia about the neutral axis plus the area of the shape times distance squared. And this area A is the area of the cross section. What this says, so look at this formula. Can area ever be negative? No. Can d squared ever be negative? No. And so what that says is the area moment of inertia is the smallest if you're taking it about the cross section's neutral axis. Any other axis besides the neutral axis, this value is going to get bigger. All right, so let me do an example. Okay, so let's say that we have a beam like this. The shape of a T. You picture that, and let's say that we're doing this problem with the x-axis along the beam's long axis, and the y-axis is up, and then the z-axis has to be this way. Okay. And let's say that, we're loading this so it's going to be bending about an axis parallel to the z-axis. Okay. That's the way we're usually going to orient the coordinate system for problems like this. And for the cross section, let's say we have the dimensions let's say this is 0.5 meters. And let's say this is 0.5 meters. And the thickness everywhere is, so I'm going to say the thickness is the same everywhere, and it's 1 centimeter. And we want to calculate the area moment of inertia about the neutral axis, because that's what we would use to calculate the stresses in this beam. Okay, so the way we're going to do this is we're going to break this shape up into 2 rectangles. I'll do one rectangle like that. I'll call this rectangle 1, and this lower one I'll call rectangle 2. If we use the rectangle formulas for these, notice that we have, so what the formulas give us is the area moment of inertia of 1 about the neutral axis of that horizontal rectangle. And the formula for the area moment of inertia of 2 is about the neutral axis of that vertical rectangle. Neither of those is the neutral axis of the whole shape. So what we're going to have to do is calculate the centroid of the whole shape, use the formulas to calculate the individual area moment of inertias of the 2 individual rectangles, and then use the parallel axis theorem for each of those to move the axis from the centroid of the individual rectangle to the centroid, the neutral axis of the whole shape. Okay, so I'll start with 1. Let's see. So let's first calculate where the centroid is actually. So the y position of the centroid, we don't have to worry about the x position of the centroid because this thing, it has a line of symmetry right down the middle. So all we have to worry about is where the height is of the centroid. And that calculation is 1 over the total area of this shape, which comes out to be 0.01. You can do that area calculation and check that. And then we'll multiply that by the area of the top rectangle, which is 0.005 meters squared. Times the vertical height of the centroid of the top rectangle. And now, okay, so we have to choose a location for this coordinate system. Let me put the coordinate system here. for now, um, for calculating where that centroid is. Whoops. So yeah, let's do it like, we'll think of this as a separate coordinate system. And actually, we don't even need this one. I guess the z-axis would go this way. But let's think about this as a separate coordinate system from that red coordinate system. All we're using this for is to calculate what the y-coordinate is of the centroid of the whole shape. Okay, so in that coordinate system, where is the y-centroid of rectangle 1? The thickness is 0.01, so the centroid is 0.005. And then we're adding that to the area of the bottom rectangle, rectangle 2, times the centroid of the bottom rectangle. So where would that be? That would be a y position in this green coordinate system of negative 0.25. Again, if you don't get any of this, pause it, do this calculation yourself and make sure that it's making sense. But when you go through all this, you get a centroid for the whole thing of negative 0.1225 meters. So the centroid of this T-shaped cross-section is 0.1225 meters below where I have that green origin drawn. Okay. So now we can use the parallel axis theorem and the formulas for the rectangle to calculate the moments of inertia. So the area moment of inertia of the top rectangle is, so we're going to use the formula 1/12 times the base of the top rectangle, that's 0.5, times the height cubed, the height is 0.01 cubed, but that would be the area moment of inertia about the neutral axis of that shape itself. So now we have to figure out how far you have to go from the neutral axis of the individual rectangle to the neutral axis of the whole shape. So we'd have to go down 0.005 from the centroid of the rectangle to get to the green origin, and then we'd have to go down another 0.1225. And so we have the parallel axis theorem says multiply the area by that distance squared. The area of that rectangle is 0.005. And the distance is 0.1275 square, then we square that distance. And for this, we get the answer we get 8.13 times 10 to the minus 5. Okay. And now we go to the second rectangle. The area moment of inertia of the second rectangle about A, the neutral axis, the axis that we want, the neutral axis of the whole cross section is 1/12 times, now for this one, the base is 0.01, the height is 0.5, and then for this one, the distance, the area is still the same, so the area times the distance squared from the centroid of that vertical rectangle to the centroid of the whole shape. Well, it turns out that that's going to be the same as this. It would be 0.25 minus 0.1225, and you get 0.1275 squared. Calculate that, and you get 18.53 times 10 to the minus 5. The units for all of these in SI units are meters to the fourth. And now, since we have these calculated about the neutral axis of the whole cross-sectional shape, we can finally come up with our total answer, which is the sum of these two individual area moments of inertia. And you get 2.6 repeating times 10 to the minus fourth meters to the fourth. Okay, so that's the process of taking a shape that's built up from simple shapes and using the formulas of those simple shapes and the parallel axis theorem to calculate the area moment of inertia for the complicated shape.
So back to stresses and beams. And the idea is that the total stress tensor is going to be equal to the stress tensor due to tension compression plus the stress tensor due to bending moment plus the stress tensor due to shear force plus the stress tensor due to torque. So far, we've only been talking about stresses due to tension compression and bending moment. And so for stresses due to bending moment, there are some restrictions, and this stuff is important to keep in mind on what we can use this for. It's not, the thing that's sort of a bummer about these restrictions is it doesn't end up being that important for the most part in classes because I tend to give you problems you can solve, But if you're thinking about applying these techniques to something that you see happening or that just comes about naturally, you need to keep these in mind. So the requirements, so this approach is applicable for, what are the restrictions? That's right. I think that's the one that we usually called number 2. Straight or close to straight. Straight is best. Prismatic, and then what's the third one? Yes. And if you have those, then the stress due to bending is a normal stress in the x direction, and it's equal to negative my over I. And you don't have to think about the sign. You can just trust the sign in the formula. And so I'm going to do an example problem. One thing to, well, yeah, let me write this and then. So notice tension compression and bending moment are the only internal loads that cause normal stresses. And, you know, in our beam coordinate system, so remember that's one where the x-axis is along the beam, the y-axis is, you can think of that as perpendicular to the axis of bending, and the z-axis is out towards us. So only knowing these, we can now fill out, you know, in other words, we can give full normal stress elements just from adding the stress tensor due to tension compression and the stress tensor due to the bending moment. Okay. That's not true of any coordinate system, because remember that you can, any crazy stress tensor, you can find a coordinate system that only has normal stress elements. But in this beam coordinate system, these are the only ones that contribute normal stresses. Okay, so we can start to do problems, we just can't fill out the whole stress tensor yet. And if you have, we can do whole problems as long as all you have is tension, compression, and bending moments. So let's do an example. So let's say we have a cantilever beam, and we have force of, let's say, 1,500 newtons and a couple of 200 Newton meters. Our coordinate system is going to be x along the beam, y up, z out towards us. And the cross section this is a square cross section where everything is 0.2 meters. Ooh, that's a fat cross section. Okay, so this is like looking from where it says 1,500 newtons down on the beam. So the x-axis is coming out towards us. y-axis is up, and the z-axis is this way. And we want to know what are the stress tensors for different points on the beam, in the beam. Well, we can do this full problem because when you calculate the internal loads, there's only going to be compression inside the beam and bending moment. There are no downward forces producing shear forces or no torques. So the first thing we need to do is calculate the internal loads. We can't do problems with beam weight included yet because that produces shear forces. Oh, and let's just make sure, does this beam meet all the requirements that we need to calculate the stresses due to bending? It's straight, it's prismatic, and it's symmetric about the y-axis, so this is good. So we have force vector, I'll call it RA. We have a reaction couple, MA, and over here we have 1500 newtons and a moment of whatever I said, 200. So Newton's second law says RAX, RAY plus negative 1500, 0 is equal to zeros. So RAX is 1500, RAY is 0. And then we only need the moment equation about the z-axis. Since everything here is a couple, it doesn't matter what the about point is. So we have MA minus 200 is equal to 0. So MA is equal to positive 200. And now we'll go to the cuts. How many cuts do we need? Just one, yep. And I guess I didn't give a length, but let's say the length is 1 meter. Not gonna affect anything. So cut 1 is for x values from 0 to 1. We have a force of 1500 and a moment of 200. And then we have the internal loads, T, V, M. I guess I'll put the torque in there too. So Newton's second law says 1500, 0 plus T negative V is equal to zeros. T is equal to negative 1500 and V is equal to 0. And then the moment equation, since I have the torque in there, I'll do it first about the x-axis. The only thing producing a torque here is that internal torque. So we just have internal torque is equal to 0. And now we'll do the moment about the z-axis. The left end, we have a moment of positive 200. At the right end, we have a moment of positive 200, the bending moment. And so the bending moment is equal to negative 200. Okay, so now we have to use these one by one, calculate stress tensor due to the tension. So let's do that first. Well, we're just going to have an x normal stress, and that's equal to the internal tension at each point divided by the cross-sectional area. The internal tension at every point inside the beam, except for the ends where we're not able to calculate anything, but St. Venant's principle says that's all right at the other places. We have negative 1,500 divided by 0.2 squared. And we get a value of 37,500 pascals. That's pretty small. Negative, thank you. Yes. Mm-hmm. The normal stress? No, you would think that seems like a pretty reasonable guess, but it's actually just the x, y stress that's non-zero due to shear force. I mean, I guess it makes sense if shear force would produce a shear stress. So in that sense, yep. So we haven't talked about it, right? So for us right now, if you have a problem that has shear forces or torques, all you can do is you can figure out what we know how to do on the normal stresses, and everything else is just unknown still. Yep. Yes, that's right. You'd have to do the two cuts, and then you'd have, like in this case, if I had put another horizontal force, like a horizontal point force, at the midpoint of the beam, and on the first half, we'd have one, XX stress, and on the second half, we'd have a different XX stress. But inside those two halves, every point has the same stress due to the tension and compression. Okay, so the stress tensor due to tension is negative 37,500. It's a very low stress. And now we just do the same thing for the bending moment, calculate that stress tensor and add these two together. All right, so first thing we have to do is, so what the formula we're gonna use is that the XX stress is equal to negative my over I. So we need to calculate the area moment of inertia about an axis going through the centroid. And that's just a formula we have. We don't have to use the parallel axis theorem. So for this shape is width times height to the third over 12. So that's 0.2 times 0.2 to the third over 12. And you get a value of 1.3 repeating times 10 to the minus fourth. Everyone's falling asleep today. I can see everyone nodding off. Get it together. Yeah, not a foghorn. That would be, I'd be like, wow, I really expected an air horn there. How do you get that foghorn in here? Foghorns are like the things they use in Scooby-Doo when they're out on a boat in the fog. Is that still here? Oh, okay, shoot, that won't work. Okay, so the bending moment is the same everywhere. And so our XX stress is equal to, what was it, negative 200? So negative of negative 200 times y, and I'm going to leave y in as a variable for now, divided by 1.3 repeating times 10 to the minus fourth. And so you can think of this as, I don't have it written this way. Can someone divide that out? 200 divided by 1.3. 1.5 times 10 to the seventh, and then times y. Okay, so okay, yes. So the cross section now. So I'm going to always draw these cross sections looking down from the right end of the beam to the left end. Okay, so I'm sitting at the right end of the beam, looking down the barrel of the gun. So the x-axis is out towards us. The y-axis is up. The z-axis is this way. And how do we decide where the origin is? Because we're just talking about the y value up, down. So it matters where the origin is. It's the middle. It has to go through the centroid. Okay, the z-axis has to go through the centroid. Okay, so the points here are positive y values, and the points this way are negative y values. So where is the bending moment smallest? So, well, don't say anything yet. So sigma xx due to bending moment, due to, write it as m, varies with y. For this problem, where is sigma xx due to the bending moment a minimum? minimum. So, I mean, we have this formula here already. You can just use this one. So it's going to be a minimum when you have the biggest negative y value, biggest absolute value. So at y equals, well, what's the biggest negative value of y? Yeah, negative 0.1, exactly. So sigma xx due to the bending moment is equal to 1.5 times 10 to the 6 times negative 0.1. And so that's negative 1.5 times 10 to the 5 pascals. I'm just asking a few different, I think the easiest way to think about it is just where's it a minimum, where's it a maximum, where's it 0? Okay, so now where is this thing equal to 0? Yeah, it's at y equals 0. And where did we put our origin? At the neutral axis. That's what the neutral axis is, you know? That's the place where the length doesn't change, and so there's no normal stress. Okay? So that's always the case. That's a definitional thing. And then the last one, where is this thing maximum? That's going to be at the biggest value of y. So positive 0.1. And at that point, because of the symmetry here, sigma xx m is equal to positive 1.5 times 10 to the 5th pascals. Yeah, it doesn't always have to be symmetrical that way. If you think about a triangular cross section, the neutral axis is only a third of the way from the base to the top. And so at the peak of the triangle, you have a bigger positive y than you have a negative y going down to the bottom. So in that case, you'd have, you know, it wouldn't be symmetrical this way. Okay, so our stress tensor due to bending moment is, I'm just going to go back to this formula. 1.5 times 10 to the 6 y, 0, 0, 0, 0, 0, 0, 0, 0. Okay, and so now the total stress tensor is whatever that small value we had for, so we're just going to add these two stress tensors together. The one for tension plus the one for bending moment. And we can write that as 1.5 times 10 to the 6 y minus 37,500. And that's the XX element. And then zeros everywhere else. Well, there, you know, so that's just a formula that tells us. So now it's just a question of, yeah, I mean, we're going to do that, like see what the minimum and maximum values are. But this isn't really, I mean, each one of those y values represents a line of points. And this tells us what the stress tensor is on that line of points. But yeah, uh, it does make sense, I think, to figure out what the maximum and minimums are. So, um, so again, how did I write it before? So first, the minimum. Sigma xx. Well, that's going to be at, yeah, so when y is equal to negative 0.1, we're going to have a value that's equal to, well, I guess we can just use what we got before, negative 1.5 times 10 to the 5 minus 37,500. So that's 15, what is it? Okay, so negative 1.875 times 10 to the 5th. And then where is it? 0? Well, that's not going to be the neutral axis anymore because we're adding two things together. So, so what we're going to do is we're going to take that whole formula, 1.5 times 10 to the 6 y minus 37,500 is equal to 0. And what's y equal? 0.05. 0.025 meters. So now in this case, it's just above the neutral axis. And then last, the maximum. So that's going to be at y equals positive 0.1. And then we have 1.5 times 10 to the 5th minus 37,500. And this time we get, what, 1.125 times 10 to the 5th pascals. So there are a lot of cases where the symmetry, there's sort of a natural symmetry that comes from the bending moments, depending on how high or how much higher, how much above the neutral axis you are or below the neutral axis. The tension compression messes that up when you add the two together because the tension compression doesn't change as you go up and down. Okay? And so that's why in this case, we have a bigger absolute value at the minimum than we do at the maximum. And that's something you can take advantage of in some engineering environments. If you know, for example, like you're going to have this beam in how does that work? I don't know. I'll talk about that later. But there are cases where like you can, so like if you want to control the stress due to bending in some way, you know, you're worried about the stress due to bending being too big for this thing, you can apply tensile or compressive stresses that offset that bending moment at a certain place. That's called preloading, and you can sometimes use that to make your thing stronger, you know, in the application it's used for. All right. Any questions about that? By putting it under stress, a certain kind of stress, you're making it more able to withstand its natural loading environment, you know, because you're applying a kind of stress that offsets some of the environment, the stress that comes from the environment. Now let's, the next one is stress due to shear force. And this is always going to be an XY stress element. It makes sense if you think about it like this. So let's say this is, we're looking at a beam from the side. And let's say this is the X location where we're trying to see what's going on. And let's say that we're looking at a set of stress elements like that, okay? Can you see what I'm trying to draw here? Well, the shear force looks like this, right? And so that naturally, and that's naturally going to correspond to tractions like this on those little stress elements. And since our coordinate system has the x-axis that way, the y-axis that way, and the z-axis that way, those little stress elements are on the x face in the, if you have a positive shear force, right, if this is V, then these are going to be, I'm not going to write it on there because it'll look clever, but these are going to be XY stress elements. See that? They're on the, so, you know, take one of these stress elements out of this strip, okay? These downward blue arrows are on the positive X face, and they're aiming in the negative Y direction. And so even though there's a sign we have to deal with, the signs are going to be flipped, but you can just see that that shear force is just intuitively contributing to a XY stress. I know you can see that. Don't act like you can't see that. That's what I want. That's great. Okay, beam requirements. for this approach to calculating the stress due to the shear force. Well, there are only two shapes that we can deal with. The first one is a rectangular shape, a rectangular cross section. And we also, for these results to be good, we need the height to be greater than the width. It's actually sort of the bigger the width is compared to the height, the worse the results are, and it's a sliding scale. So our best results are if it's really tall and skinny, and and if it's a square, I don't really know how far off it would be. I could calculate that. But if you have for our purposes, let's just say square is the widest and shortest that we're gonna take as acceptable. Okay. And the only other possibility, so rectangular, and then the other possibility is a circular cross section. Well, with a rectangular cross section, we can do it at every y location along the cross section. With a circular cross section, we can only do it at the neutral axis. But only along the neutral axis. Well, that sucks. Might as well not know anything about it then, except, well, it turns out that the neutral axis is where the stress due to shear force is the biggest. So if you have a really significant stress due to shear force, at least you can figure out what it is at the maximum. That's where it has the greatest absolute value. Okay, so notice what's happening here. We didn't have any restrictions on the stresses we could calculate due to tension compression. But for the bending moment, we had some pretty strict requirements. And now for shear force, we have some strict requirements. And so if you're looking for beams where we're going to be able to calculate the entire stress tensor, we're going to have to take like the intersection of all of these requirements. It's not like we're taking like you're adding like taking this extra space, the space you get from the bending moment requirements plus the space of solutions of allowable cross sections that you get from the shear force. You need things where they both apply, And so notice, that was so badly said, but notice with each new set of beam requirements, the options for acceptable beams are getting reduced. So now if you have a internal loads problem where, so you solve the internal loads and you get bending moments at the point you're interested in, and you get shear force at the points you're interested in. Now you can only calculate the stresses if the thing is a rectangle, or if the thing is circular, but then you can only do it at the neutral axis. All the other things that were allowable for calculating stress due to bending moment have now been thrown out. Okay. And it has to be straight, and it has to be prismatic. I'm just trying to stress how important this stuff is to consider, like when you go out and you look at, like in dynamics today, when like we looked up and we're like, oh, I wonder what the stresses are on that thing. You got to think like, is that panel straight? Is it prismatic? Is it rectangular? Is it, and you have to go through each one of these. And if it doesn't meet those criteria, then the approaches that we're using, you can't do it on that. Yes. Well, really like you would. So if you knew a lot about this stuff, like more than I know off the top of my head, you could come up with some simplifications that would give you some okay answers for it. But really the short answer is you would go to a finite element software package and you would type in the external loads and it would spit out these answers at you. And the hand calculations that you do using this simplified approach or whatever would only be used to sanity check your answer. Like, do I believe that the computer solution, came out without dividing by 0 or whatever? You can sometimes get wacky things in the computer simulation. But the final answer to any kind of like real application is you would get the stresses and strains from finite elements. And all we're doing is just sort of trying to understand in a way like how to interpret that stuff and how to sanity check it. That's all we're learning this stuff for, really, and except for the handful of people who will go into writing finite element software, So before we can, the formula for the stress due to shear force is tau xy. So that's the shear stress in the xy spot is equal to negative. So again, the sign will work itself out for you. V times Q over I sub B. And so we're going to have to define what this Q means. And we'll be able to use that formula. No, it's not. It's different. It's just one of those times where you have more mathematical things than you have letters in the alphabet. So, and remember with bending moment, I'll say one more thing. I can say this again next time, but with the bending moment, by thinking about how the shape, like you bend a bar like this, and then you can intuitively figure out that the top of that bar that you bent is going to be in compression and the bottom is going to be in tension. You can figure out intuitively why this negative sign is here from this picture, because this is what, with our sign convention, this is what we call a positive shear force. I don't know whose idea that was, but that's what we do. And a positive shear force corresponds to downward XY stresses, but downward XY stresses on the X face, that's in the negative Y direction. And that's why those are opposite of each other, the sign. Okay, any questions? All right, so we'll finish shear force next time. Yeah, exactly. Except it's not even, I think that somebody was, that one's even funnier in a way, I think, because